All right, can somebody confirm that you can see my screen and that you can hear me?
Yes, ma'am.
Yep.
Okay, excellent. Okay, I think I have hit, okay, so I know 2 people sent me homework that they could not upload to Gradescope. I have those. I haven't sent you confirmations. I see them though. And I think when I just looked, 21 people had been able to upload. So that looked like it was in general going good. Okay. Let's see. I have Jack, if you're on, I know I still owe you an email, but otherwise I think I've addressed most stuff that came up for today. Okay. So my plan is we want to finish off this fin of uniform cross section, and then we'll start some lecture 5 notes. You have, when is your exam is not till next Monday. Okay, so we'll talk about it on Wednesday. Okay.
Real quick though, is that going to be an in-person or a?
Oh yeah. It is in person.
Okay.
So Luann has reserved the classroom, and then there's a conference room across the hall so that you can be reasonably spread out. So it is in person, and it's an unusual time because we needed to start later because you have your week of learning. Okay. So this longitudinal fin, we have properties for it. I said last time, the little head start we had was that we were going to take a look at this M parameter that is a combination of a heat transfer coefficient, P for perimeter, or thermal conductivity, and cross-sectional area. Okay, let's go back to, okay, our first thing we're supposed to do is to solve for thermal efficiency. But as I start thinking about it, assumptions, let's hit these. When we talked about fins, we're always looking at steady state conduction through the fin. Always constant properties. We don't have volumetric heat generation, but I think that would be unusual to think that we might. And then we're going to assume, does it say here explicitly? Okay, we're going to assume an adiabatic fin tip boundary condition. Okay. We saw that table the other day, and it had different boundary conditions for the tip, but I'll tell you that adiabatic is pretty common. And so if I wasn't given any information, I'd use the adiabatic case. And then we're moving into a little bit more unusually shaped fins. And there we only have the option for the tip of the fin to be adiabatic. So fin efficiency is how much the rate of heat really removed by the fin, and then what we call a maximum amount of heat removal in the denominator and the maximum is the whole fin surface was at the base temperature. If we looked back in the table for an adiabatic fin tip, we got capital M, which is defined in terms of some of these things we're seeing over here, the heat transfer coefficient and cross-sectional area. We'll look that up in a minute. And then hyperbolic tangent of little lowercase m L. And I put my note in here. This is equation 3.81. So we didn't do development now. We're just pulling it from the table. And then for the maximum heat removal from the fin, it's H and surface area of the fin. And I wrote it as theta B, but you're thinking that means the temperature of the base minus T infinity. We did this the other day in class that we went through what M is, and we canceled out some terms. We can get to this reduced expression for fin efficiency. Okay. And now let's do this part over here that we had set up, how to calculate M. So we talked about why it can be approximated as 2 heat transfer coefficient divided by KT. And let's substitute numbers in. Okay, and I am looking up just to feel good that I have substituted things in right. Heat transfer coefficient, oh, there's the K, and thickness is 9.5 millimeters. Okay. The units for M come out to 1/meter. Okay. I usually carry that through. And L is going to be, we do have a picture of the fin, but L is going to be this distance. Ooh, okay, there we have it. 100 millimeters. So when I plug in numbers, has anybody tried using hyperbolic, cosine, sine, or tangent on your calculator?
Not recently.
Not recently. Okay. If you can try it out just to see that you got it. I mean, we can have some workaround. I think I can do a table, but I usually have you do a fin problem at some point. It wouldn't be on this upcoming test, so don't get concerned about that. But at some point, and it would be helpful to get a little bit of feedback on how many people can figure out where hyperbolic tangent is on your calculator. So this was our first thing to find out a fin efficiency. This isn't great. We talked about we'd like to have a higher fin efficiency, a relatively high fin efficiency. It doesn't have to be 95%, because that probably means we made the fin too long. And that last bit we're not getting some efficiency out of, but 50% might be a little bit on the low side. Okay, the next thing it asks is to find fin effectiveness. And in words effectiveness, it's still QF on the top. So the rate of heat removal by the fin. But if we slice that fin off, it's the heat removal by that base area without the fin. Boy, and I don't know how to write that in symbols. We could put HA cross section T base minus T infinity. So again, you're thinking rather than looking at the whole surface area of the fin, I sliced it off. Okay, I think we did this the other day that we showed for a uniform cross-section fin with an adiabatic fin tip, that for that particular case, the effectiveness looks like PK over HAC. And we have so many, oh wow, what did I do here? I'm not full screen, sorry about that. I keep looking, so M, what did M look like? HP over KAC, HP over KAC. Yeah, it's not the same thing. I just keep it, so many of these combinations roll around here, but that is not our little M. Okay. So we're going to have to put together this combination of terms. Okay, for perimeter, 2, and then I'm taking width plus thickness, and thermal conductivity K, and then over H, and cross-sectional area is W times thickness. Okay, and just scrolling back to that picture for a minute. So this is my perimeter. 2 thickness times width. I got to have 2 thicknesses and 2 widths. And then cross-sectional area, okay, is thickness times W. All right, and just like we did the other day, the width, we said it's going to be really wide. And in comparison to thickness, we can drop thickness off. And then we have a W in the numerator and a W in the denominator. Now we're going to cancel those out. I have 2K over HT. If I plug in numbers, this one ends up being unitless. So no units to carry along with this one. Okay. And then hyperbolic tangent. And I'm just going to put this combination here. It was 1.7 1.76. Okay, and we got an effectiveness of 11.2. And this is a pretty high effectiveness, so we would not. This is a fin we would consider using based on effectiveness. We said that it should have at least an effectiveness greater than 2. Otherwise, it's not worth paying them the cost to put the fin on. Okay, the third thing said find the temperature at the tip of the fin. And so that means we want to use the temperature profile. And if we expand this out, we're going to think through that this theta is temperature that we want. We're going to say at the tip of the fin minus T infinity. That's theta. And then I'm taking theta b to the other side. That's temperature of the base minus T infinity. And then I have to multiply by these, that ratio that we have listed, hyperbolic cosine of this whole thing, ml minus x over ml. Okay. Oh yeah, but then we want to think through that since we're looking at the tip of the fin, so we're looking at x equals L. Okay. So I want to put x is equal to L. So we get a hyperbolic cosine of 0. Okay. And I wouldn't know what that is off the top of my head. I usually ask, and somebody in the class remembers that hyperbolic cosine of 0 is equal to 1. Okay, so this whole thing is equal to 1. So let's write T, the tip, so x equals 0, minus free stream temperature is 50 degrees C. And the base temperature was 90 minus 50, 1 over hyperbolic cosine of 1.776. And we can solve for a temperature at the tip of 63.2 degrees C. And just so we thought through, this math that we did, the base temperature was 90. We picture that the temperature's decreasing as we move down this fin. Okay. And if we got something cooler than 50 degrees C, well, that would be pretty suspicious. But we got a tip temperature of 63.2. Right, the last thing it says is the heat removal rate by the fin per unit width. So now we're thinking about if I made this thing, so here's our width. If I made it 2 meters versus 1 meter long, how much heat removal rate am I getting? So we had this equation, we used this a little bit earlier. And again, this is for a fin of uniform cross section and an adiabatic fin tip. Okay. This we can carve out what we want to come up with. Is the rate of heat transfer divided by that unit width. So divided by W, and let this QF prime. We could do some work and pull a width out of that M factor. But I'm going to suggest that we have this other option. Let's work down another path. So this equation I've just written, it's just the fin efficiency equation rearranged. So it says QF is fin efficiency times the QF max. Okay, and I want to expand out the maximum heat removal from the fin is a heat transfer coefficient, area of the fin, and then T base minus T infinity. Okay. And area of the fin I can replace with, I'm going to put eta in again, a heat transfer coefficient. So area of the fin, I have 2 L and times W. And I usually like to think about that. So I'm going to scroll up to my picture again and think about this fin area. Well, we could just go right here. Okay. Okay. So this fin area is really, really long. We're going to say in this width direction. So this is an L times a W gives me the top surface of the fin. And another L times W for the bottom surface of the fin. We say if it's really long, I'm neglecting. We're going to neglect this surface area. And on the back face too. Okay. And then because it's an adiabatic fin tip, I'm neglecting that surface area. So all we're including, it's a little bit of an approximation again, but we're just including the top surface and the bottom surface area. Now we're in, oh yeah, we got to finish off T base minus T infinity. Okay. Now we're ready to do our idea that QF prime is QF divided by width if I plug in numbers, our efficiency was 0.532. Heat transfer coefficient, 50.2. Watts per meter Kelvin. 2, a length of the fin from the base, it was 100 millimeters or 0.1 meter. And then base temperature, 90 degrees C, free stream temperature, 50 degrees C. Oh man, I have done this a million times. So I'm looking through units. I don't like my units. It's because I got my heat transfer coefficient. I forgot the squared there. Okay. So I should have watt per meter, and I like those units. So that cancels out. We got one of the meters canceling out. sorry about that. Why did I do that again? I want to do. Okay, so I want to make this figure look a little bit bigger. Okay. So on this this top graph, it says dimensionless heat flow into the fin. So they have non-dimensionalized that. That would be our QF. And they've non-dimensionalized it with this maximum heat transfer. So this really is back to our fin efficiency. And on the x-axis, they have plotted this combination of M times L. L, you're thinking it's the length of the fin. M has incorporated in it, a heat transfer coefficient, thermal conductivity, so a few things in there. Okay. And what they have shown is how hyperbolic tangent of ML varies. And we saw the other day that that function is bound by 1 and -1, and we really only care about the positive portion of it. Okay? And it shows that by about the time we get to ML of 3, so a combination of these features of the fin and the length of the fin of 3, we get to about the highest fin efficiency we can get, about 1. Oh, and I'm doing the wrong thing, aren't I? I'm doing the wrong. Well, we're looking at hyperbolic tangent gets to about 1. Okay. This other curve is relating to dimensionless temperature at the tip of the fin. So if I made this bigger, temperature at the tip minus T infinity over T base minus T infinity. Okay. So as we get to a longer and longer fin, the tip temperature is almost T infinity. So now we're looking at this curve. So it drops off pretty significantly. This non-dimensional temperature gets very close to 0 as the fin gets longer and longer. So these are both features that you may expect. Part of the point for this is to think about what an infinite fin means. And this second figure, they're plotting dimensionless temperature again. So this is what we have up here. And they're showing that at a combination of M times L of about 3, this dimensionless temperature gets all the way down to 0 by an ML Nope. Sorry, this is zeta, X over L. Sorry. That I reach the free stream temperature at the end of, at the tip. I have again, this case we're talking about, that I've gotten to free stream temperature. My non-dimensional temperature is 0. I have no driving temperature difference. The end of that fin is doing me no good. So this combination of M times L, it says, has the note, it's over-designed. I don't need all of that fin material. An ML combination of maybe 3 is a pretty good approximation of an infinite fin. That's a reasonably well-designed fin. You get reasonably close to T infinity, but you're still driving heat at the tip of that fin surface. This is a little bit of an aside. In the review paper that you recently finished it, 2 weeks ago. I maybe just graded it a week ago. Okay, and we had this flat plate, and they posed a certain temperature on one end and another temperature on another end. And they gave us some information about the dimensions. And I do not remember all of the dimensions, but one of them was, so maybe this was like 100 millimeters and this was 50 millimeters. Oops. And then I think the thickness was 5 millimeters, so even thinner. And they said something about that they were ignoring convection effects. Boy, I forget what the phrasing was, but a number of you wrote something about, like, what does that mean? Why did they say that? Or you commented on it. And this kind of fits in our fin analysis section. And I only put this together, I don't know, last week, thinking about this. Okay, so if we picture this as kind of our fin, we're conducting heat away from this higher temperature to this cooler temperature, and there's convection going on all around this. And what these people wanted to do in that research paper is they wanted to be able to neglect temperature effects and get a nearly uniform temperature at each location. So let's say, I kind of forget, if this was 60 degrees C and this was maybe 0 degrees C, something like that. That maybe I have 50, 40, 30, that rather than having it cool down at the edges and I have some curved temperature profile, that I'm choosing a thickness and heat transfer coefficient combination such that I have nearly uniform temperature. So this is our idea of convection only in the x direction. Okay. And we said that that's one of the things we assume in the fin approximation, that we just have temperature is only a function of x direction, conduction only. That's what they wanted to do in this. There is a test for when you can assume one-dimensional conduction. It involves the BO number, which we see conduction. Okay. But one way to think about BO number is resistance to conduction over resistance to convection. In this slab of material and fins, both of these cases, we'd like resistance to conduction to be small. So we want this to be like easy for heat moving in this direction as it conducts to the outside. As I picture, I've got convection occurring off this surface. So I've got heat conducting in this direction, but it also has to move to these outer walls where convection is, outer surfaces where convection is occurring, that I'd like to have a low resistance to conduction. Otherwise, the case where if I have a lot of resistance to conduction, I pull heat out of this surface and I can't recover it. So the surface cools down faster. Let's see, maybe we want to do surface cooling down faster. And the center stays warmer. Okay, but if I have low resistance to conduction, that can all even out. I got convection occurring, but I can have conduction occurring quick enough that it can make it out to make a, to this outer surface and keep a uniform temperature distribution. And then resistance to convection. Okay, so I want this to be kind of high. Oh, no, I did it the wrong way. I want this to be low. And I want resistance to conduction. It needs to be relatively high. It doesn't have to be super high. Okay, so we don't want to be able to pull heat out of this surface so fast that the heat can't spread through the material. And then if I look at what resistance to conduction looks like, so in my picture, this is my center line. And I'm going to pick the plate sitting down, and this is my 50 millimeter thickness. Heat moving along at most has to travel through half of the plate. So it has to conduct through half the plate. So I'm going to put this, I'll put a T here. It's got to be T over 2. So that's my thickness. And then over K times cross-sectional area. That should look like the conduction resistance that we have talked about in chapter 3. And then my resistance to convection. Now I'm looking at how I pull heat out of that surface, and the resistance to convection looks like 1 over HA. And these both have the same surface areas. So if I rearrange this, it looks like HT over 2K. And I want this to be a small number. And the rule of thumb is that you want it to be less than 0.1. So for that plate that said it was 50 millimeters, so I'm going to try this for the plate. Okay, so, well, let's follow my order. Let's do HT over 2K. Okay. So I'm going to do 50 millimeters. And I need a 2 in the bottom. Okay. I had to do a little bit of thinking. So, they didn't say anything about the convection, and free convection in air is between 2 and 25. And so for, just getting a ballpark number, I'm going to put 6 as my convective heat transfer coefficient. I'm estimating this. And then for carbon steel, the thermal conductivity, 60 watts per meter Kelvin. Okay, so I kind of picked these two because I like getting rid of those 6s. So this had quite a small BO number. And if we, again, think back to what that tells us, is that we would expect to have that nearly uniform temperature distribution across. That temperature is only a function of X direction. It's not a function of the Y direction. Okay. And again, this is a rule of thumb. It's not going to be exact, but it gives you an indication that they picked a geometry that allowed them to assume one-dimensional conduction. Okay, and I don't know, because you guys can't see, but the sheer excitement of thinking, I picked that problem with no thought that we would be like working on fins next. And there, as I read your comments, are like, why did they say that? And it's like, bam, because we've got this method for looking at when one-dimensional conduction is appropriate. I am ready to move to lecture 5. Oh, let's put one more note. Okay, so it's a good approximation. Now I'm ready to change to lecture 5 notes. I don't know why I repeated that slide. You have seen it before. I don't think we need to say anything more. These are the 2 cases that we have spent a little bit of time looking at. Okay, and just to remind you that this is for a uniform cross-section. Because now we're going to loosen the constraint on having uniform cross-section. And here's some typical fin types. And A is a straight uniform cross-section fin. B is also a straight fin, but it's got a new non-uniform cross-section. So we want to think about, as we're moving away from the base, that its cross-sectional area keeps changing. C is an annular or radial fin. And this one you can think about too, its cross-sectional area is changing. So as we move away, now we're moving in the R direction. Okay. So this fits in our case of non-uniform cross-section. And then D is pin fin. Okay. And we could have pin fins that have uniform cross-section. So you just think if I, here again, I'm moving in the plus X direction and the area is changing, but I could have cases where I just have this nice little wire or cylinder shaped fin. Okay, we are talking about theoretical analyses for these, because I always think about, I know that you work with some finned surfaces at GE, and those are not going to be amenable to these simple analytical models. You're going to rely on, likely, like you are relying on some experimental data to come up with fin efficiencies or figure out how much heat removal you get. Okay, the one that we're going to spend some time with is this radial fin. Okay, and we're setting up the geometry that we're going to have, some radius. We've got, picture we had a tube. Maybe we have fluid going through the center of this tube. It's open. And we have placed a fin on the outer tube surface. And maybe from this first radius, or the outer surface of the pipe, that's an R1. Okay, so maybe I'll go from here to here, and I'll call that an R1. And then maybe a good place to draw this is an R2. And then R is just our coordinate that we can, a directional coordinate. When we did the first fin, that was a straight fin moving in the X direction, we set up a balance, an energy balance. And for this radial fin, our balance is going to look like. So if I took a little slice here out of this, you think of QR, I'm conducting heat through the fin, I'm conducting heat, through this little VR element. And then over that surface area, I also have convection going on. So I have heat being conducted into that little element, but then I have two paths. It can be conducted out or it can be convected away from the surface. Okay, and we've been doing so many things where the temperature gradient's in the X direction. Well, we haven't done a ton, but just thinking through, now we're going to have a driving temperature gradient in the R direction. So our driving temperature gradient now is dTdr. Okay. Boy, I'd have to scroll back pretty far in the notes, but this equation I'm going to write for the radial fin is really very similar to what we did in the X direction. If you looked back in the notes, this really looks exactly the same, except for every place I have an R here, we had an X in that first time we went through. Okay. But for our previous case, we said that cross-sectional area for our straight fin, we had a cross-section. How does cross-sectional area change with X? That was 0. We said it was a uniform cross-sectional area, but now we don't get to dump that term. So this is the case where we've got this equation, but we need to keep this second term. For the radial fin, the cross-sectional area. So we're thinking, let's put a little note over here. So that's my thickness T. It looks a little bit off, but I want you to think that, little sheet of, circular sheet I put in there has a thickness of T. And so my cross-sectional area, you're thinking about all the surface area, is 2 pi r. That gets me circumference and then the thickness. And if I take the derivative with respect to r, that just gives me 2 pi t. And if you're thinking ahead, it's the idea that we're going to substitute into this equation and then see if we can make some simplifications. One more thing to look at, we have a surface area over here. Okay, so surface area. If I think about, now I'm looking at, let's use a different color too. All right, this is looking bad, but that red, that is my surface area that I have convection occurring on. We are going to assume an adiabatic fin tip, so we're not going to consider the tip. So I'm looking at pi r squared gives me the surface area. 2 gives me the top and the bottom. Okay. But then I have to subtract off what is taken up by the pipe, that inner tube. And if I take the derivative with respect to r, I get a 4 pi r. So we're going to substitute into this previous equation. All right, and you can already see a lot of things are going to cancel out, but I'm going to follow my plan. Ooh, that's a plus sign, no, plus sign. So I've got 1 over 2 pi RT. This derivative of cross-sectional area with respect to r is 2 pi t. And I have dt dr minus 1 over cross-sectional area is 1 over 2 pi RT. My h over k I'm going to keep in there. My derivative of surface area with respect to r. And well, that's it. The t minus t infinity. Okay, we're going to do two things. And I always do this old way of let theta equal t minus t infinity. And then if I take the derivative with respect to r, I just get dt dr, and the same thing with the second derivative. And we're going to define m squared So now my equation looks like d squared theta dr squared plus 1 over r d theta dr minus m theta equals 0. And all this work was done because we got this into a classical ordinary differential equation, and it's called a modified Bessel equation. And the solution to the modified Bessel equation looks like and this I0 and K0 are modified Bessel functions. Okay. So I think this notation likely looks new to you, but just so you're thinking through, we did a solution last class, and I think this one you would have seen before. Theta x, it was like C1 e to the mx plus C2 e to the minus mx. So you got to figure out some solution to this equation. This one, again, I wouldn't come up with it, but it is a known solution to that equation. Okay, so I'm getting rid of this one. This was our old, for our straight fin. So I0, it's called a modified Bessel function. It's odd that we hit this equation first. In our development, we hit a modified Bessel. There's really a Bessel function, and we see that in another point in the course. But so this is the modified Bessel. It's given in a capital I, and whatever its subscript is, that's its order. And K is modified Bessel function of the second kind. Okay, we're going to go to these slides in just that are coming up, but we got to come back to this equation. But maybe I should be hinting, we have to apply boundary conditions, just like before. So we need 2 boundary conditions to solve for those C1, the C1 and C2 that appear there. But let's look at these. So this first slide I put in, what is it showing? Okay, so the graph is showing Bessel function, and the J is of the first kind. And the Y is used to denote a Bessel function of the second kind. And here they're using alpha to show the order. Right, so just a symbolic form to show the order. And then you can see that these graphs for Bessel function, they are oscillating about the 0 axis, or about y equals 0 as we move down the x-axis. And the second kind does the same thing, but it's unbounded as x is equal to 0. Okay. So this is the equation for a Bessel function, not modified Bessel function. Here's the definition of the Bessel function. And I want to be clear, because we have been using M, and it means some particular things. It's a combination of heat transfer coefficient, perimeter, cross-sectional area, a bunch of stuff. That is not what is here. Here, M is just an index. They're telling us start at M equals 0. So I do 0 factorial. I put a 0 in here. I raise this to the 0 power. Then I go to M is equal to 1. So here, M is an index to step through this summation. There are some really interesting properties of Bessel functions. And so instead of writing this Bessel function of the second kind in terms of an infinite series summation, they've written it in terms of the Bessel function of the first kind. There's like a whole bunch of identities and things you can do with these, but let's move on to modified Bessel's function. Yeah, I wish I didn't put the apostrophe there. Let's get rid of that. Modified Bessel equation. So that's the one that is the form we're looking at. Okay, and we had an I for our modified Bessel function of the first kind, and here's our definition. And again, it's this summation. You don't often have to do infinite series, but you do have to wait till it converges. And that you can see that these have a significantly different. So this was our modified Bessel. So this is our I here, in K here, and has a significantly different trend as opposed to the Bessel function. Okay, so I don't think I want to say anything more about these. You've seen a little bit. You know that there's some math behind them. We'll talk about how you can evaluate them rather than having to go through these infinite series in just a minute. Okay. So the two boundary conditions we're going to apply to solve for these constants of integration. At R equals R1, so that's right where the fin is attached to the outer surface of the tube, we would say temperature as a function of R is equal to the base temperature. That's very similar idea to what we did with the straight fin. And then since I really need to write this in terms of theta, and theta is temperature minus T infinity, and we're going to call it a theta B. And then the other one we'll use is at R is equal to R2, we're going to say that it is no heat loss, so it's the adiabatic thin tip case. And then again, we want to be writing it not in terms of temperature, but in terms of this substituted variable. Okay. And just reminding you, this would be adiabatic fin tip condition. Okay, and I hope you're thinking through, you know, when we have Fourier's law of conduction, so if we have no heat flux, well, K can't be 0, so this has to be 0. I think you're used to seeing that, no temperature gradient. All right, if I apply those two boundary conditions, and again, we do some math, so it's not insignificant to get to this result. Okay, I want to give a little bit more space, and then I want to write ways that you can evaluate these Bessel functions or modified Bessel functions. And the idea is that this is the argument that you are operating on, that you're taking the Bessel function of MR, right? Or we're taking the Bessel function of MR2. Okay, so one is ways to evaluate. Okay, so X in this equation is this argument MR. I don't think you are going to go back to this definition, but it's an option. Okay, so that's 1. 2, in the back of your book, we have some tables given. And math, boy, I think you're going to go to the internet, but I'm going to tell you in the old days, so like when I was in graduate school, we had math tables and we could look these things up. You have a very small subset given in the back of your heat transfer book.
And a quick question.
Yeah.
The M in our function, where we say x equals mr, that is not going to be treated as an m in that first definition, right?
In this definite here?
Yeah.
Okay, so no, you got to be careful. So this
So
is the standard.
If we substitute,
Pardon?
that's just an indexer. So if we substitute that for like an I or something, then we could say it was
Then you
I
could-
exclamation, etc.
Yes, yes.
Okay.
And then this is a gamma function. You got to figure out what gamma function is. And again, that's your index you're stepping through. And then this is back to, what is M? This is 2h over kt. So I'm sorry, but this is the kind of standard way it's written that I have here. And it has that M, and I know it's throwing you off because we've had this M that is a physical quantity, not just an index. But all of these, guys go together. Okay, but then when you are, finally putting your physical information for the problem in, that M rears its head again that we have been using. And it's a different M. Okay, and I can tell, I think you're intrigued. You're going to try this out. Okay, I'm showing you parts of this table. And the thing that I want to say is, so now what you're doing is you have to figure this argument. This argument, in our case, it's MR. And that's what's going to be in this column of the table. And it goes bound. So you may have to do some interpolation. But let's say we have 0.2. Then you look over. If I want I0, I don't know why they do it in this form, but you have to then divide it by e to the minus x to back out an I0. Okay. And you can see that we had Bessel function of the first kind of order 1 appear here. So that's why they've given it in this table in the textbook. Okay, one way, and you might like this one. Okay, in Excel. Okay, so you use equal sign to say that you're going to use some kind of, function. And then in our case, I'm going to put an I in because we're doing this modified of the first kind. But you could put J or K or Y, whichever one you needed in there. And then you put the argument and then the order. And it spits back the Bessel function or modified Bessel function.
And those are universal to I, J, K, Y.
It is. Isn't that amazing? Of all the bizarre things that I think don't get universal, but, and maybe because it's been around so long.
Okay, so the argument is just the x equals mr.
Yes. In our case, so if we scroll back up a little bit, I'm sorry, it's like these things that I have in the parentheses, you think about you have to take cosine of, alpha, or we had hyperbolic cosine of ML. We're doing the modified Bessel function order 1 of MR. So yes, MR is the argument. I am out of time for today, so I will not lecture anymore. So people who are ready to go, feel free, and I will stay a few minutes to see if I get any questions.